All right, folks, so now we're going to do some of those classic contextual or word problems using the cosine law. So let's see what we can come up with. Some real great trigonometry. We're going to apply the cosine law in novel situations. Yet another way to say the same thing. Let's do some word problems. So to make sure we don't make any mistakes, it's a good idea to go through some of these steps. So I like to call this a nice three-step process. So the first thing, same thing we did when we looked at sine law. Read and understand the problem clearly. Then we do our best to sketch a diagram with everything we know in it and label the thing that we don't know. After we have everything we know and what we don't know, we can use our typical stuff we use to check to see if the cosine law is okay, label it up correctly, set up the equation, and solve all the same stuff that we normally do with the cosine law. So the same kind of thing that we would do with sine law. Now, it's kind of giving it away a bit that the question that we're going to do here as an example of how all this works is going to involve the cosine law. But once you get good at recognize the patterns one way or another, then it's pretty simple to decipher whether it's going to be a sine law question or if it's going to be a cosine law question. All right, so let's get down to business. So here's the problem situation that we have to tackle for this one. So what we're worried about is the pendulum on a gigantic clock. Wow, that sounds kind of cool. It's 500 centimeters. It's a 5-meter long pendulum. This is a very big clock. It says when the pendulum swings from one extreme to the other, it moves a horizontal distance of 230 centimeters. Okay, that's a horizontal distance. So that's just strictly horizontally back and forth. Through what angle does it swing? All right, so we got certain length for the pendulum. Now, when a pendulum swings, it sort of goes the same distance left and then right. And I guess the distance between those two extremes is what they're talking about. Yeah, it says one extreme to the other. That's the horizontal distance. Okay, so let's draw a picture where if the pendulum, I guess we'll just draw like a little circle on the end for the pendulum, is as far as it gets in one direction, and then it should be roughly symmetric to be as far as it gets in the other direction. And if the pendulum swings all the way sort of over here, it's going to be at one extreme, and all the way over there would be at the other extreme. And it would sort of be hanging vertically down the middle if we're at its what we would call equilibrium point. Okay, so it says it's 500 centimeters long, so we've got 500.0 centimeters along here, but because of the symmetry of this thing, we're just looking at two different times, but it's the same pendulum that's hanging down here. That's 500 centimeters along that side as well. And as it swings from one extreme to the other, it moves a horizontal distance, so that's across here, of 230.0 centimeters. Okay, so that's how far we are across there. So it looks like we know three sides of this. Aha, I bet they're going to ask us for an angle, and they did. They said, through what angle does it swing? So as the pendulum swings from one extreme to the other, we go along a path like that, and this would be the angle that we're swinging through right here. I'm going to call it angle theta. All right, so that looks okay. So now we got to label some stuff up. So let's label our triangle with some good numbers and letters and things. So I'm going to call this angle A down here, angle B, and then angle C up on the very top. And then I guess we can call this side C, and then this one would have to be side B, and this one would have to be side A. And with all of that, then we've got to set up an equation that's going to let us determine the measure of angle theta. So this is going to be a cosine law setup. So we're going to say the cosine of C, which is the position that that one is in, should be equal to a squared plus b squared minus c squared, all divided by 2ab. So then we have to fill in the details for that. So it's cosine theta is what angle C is here. And that's going to be equal to a squared, which I'm just going to write as 500 squared, plus b squared, which is going to be another 500 squared. That minus c squared, so 230 squared, all divided by 2ab, so that's 2 times 500 and another 500. Okay, so then we're going to tabulate what cosine theta is going to be equal to here first. So let's just get the numerator done. In the numerator, I've got a square 500, which is going to be a lot. And then I've got to add another 500 squared, which is another lot. And then I'm going to subtract 230 squared, which is a lot. And we end up with 447,100. Okay, so 447,100. Where are we? Right here. So 447,100 100. That's a humongous number. Speaking of gigantic clocks. Then on the bottom, I have 2 times 500 times 500. Let's see. 2 times 500 would be 1,000. So I'm just going to add 3 zeros to 500, and that's going to give me 500,000. So a little mental arithmetic there. Makes that nice and quick. And then I've just got to get the cosine of that ratio. So let's see. Or the inverse cosine of that ratio. So we're going to say theta should be equal to the inverse cosine of all of that junk. So 447,100 divided by 500,000. Big numbers. Alrighty. So you can knock a couple of zeros off the end if you want when you plug that in your calculator, but either way, let's see what our calculator tells us now. 447,100 divided by 500,000. And inverse cosine of that business, we've got 26.6 degrees. So not so dramatic after all. We've just got 26.6 degrees. So what angle does it swing through? Up here, 26, almost 27 degrees. All right, so quick rehash. Remember, read and understand the problem, sketch a known diagram, then you get down to the cosine or sine law business, which in this case is cosine law. Label correctly, check for the pattern, set up the equation, solve and evaluate all that good stuff, and you'll be well on your way to a correct solution. Alrighty, thanks very much.